Hi, I am Georgios Amanatidis, and this is a presentation about the paper Round Robin Beyond Additive Agents, Existence and Fairness of Approximate Equilibria. This is joint work with George Birmpas, Philip Lazos, Stefano Leonardi, and Rebecca Reiffenhäuser. So this is a paper about fair division. Fairness is a natural objective in many scenarios, and of course, one might ask what is fair in our setting and whether fairness can be achieved. Now, we start with some basic assumptions. We assume no free disposal. For instance, we cannot achieve fairness by not giving anything to anyone. So we don't want to throw away any resources. And also we assume that we have indivisible goods. So we have items that cannot be split or shared. And we want each agent, each participant, to receive a set of items that can be considered fair from their perspective. So more formally, we have a set of M indivisible goods and a set of N agents. And for the time being, let's say that each agent has an additive valuation function, although we're going to leave this assumption. So let's say that agent I has value Bij for good J, and then given a set, they add these values to find what their value for the set is. And an allocation is a complete partition of the set of goods. And by SI, we're going to denote the bundle received by agent I. Okay, so we are going to take an envy freeness approach to what fair means here, meaning that fairness is going to be based on pairwise comparisons. So we say that an allocation is envy free if for any pair of agents I and J, agent I considers their bundle to be at least as good as J's bundle. Of course, this is impossible to achieve when the goods are indivisible. So one of the most well-known and quite easy to achieve relaxations of envy freeness is envy freeness up to one item. Or for short, it's EF1. So an allocation is EF1 if for all pairs of agents I and J, well, agent I considers their bundle to be at least as good as J's bundle if one good is removed from the latter. Usually, that can be like the most valuable good for agent I. Okay, so this is our setting. We consider agents that want to share indivisible resources, but also we assume that these agents are strategic, so they have incentives. So in our setting, truthfulness or incentive compatibility means that we have a mechanism, or rather an algorithm, that distributes the goods, and we say that this is truthful if no agent has an incentive to misreport their values for the items, right? So the reporting the true valuations is the best strategy, right? Okay, and of course the question is, can we combine the two? Can we have fairness and truthfulness together? And unfortunately, fairness and truthfulness are incompatible even for just two agents, and for additive valuation functions, for not only for EF1, but essentially for any reasonable fairness notion. So what's the next best thing one can do? Well, what about having non-truthful mechanisms, but mechanisms that have good fairness properties in their stable outcomes, meaning that have equilibria that correspond to fair allocations? Okay, so by equilibria here, I mean pure NAS equilibria, meaning that, well, if I fix the reports of every agent, no agent can unilaterally improve by deviating. So the question now becomes, can we have a mechanism, meaning an algorithm? Because here we assume no payments, right? So we have an algorithm, but the input might not be the true values, but instead the reported values that has equilibria, and this equilibria correspond to allocations that are fair with respect to the real underlying values the agents have for the items. Okay, and this brings us to round robin, because for the additive case, the answer to that question is yes. We can have round robin that always has equilibria, and these equilibria are always EF1. So let's quickly review this result. So what is round robin? This is a very simple allocation mechanism where the agents take turns, and in each turn, the agent, the active agent, is allocated their best available good. So in this particular example, where red is for player 1 and green is for player 2, round robin will proceed as follows. Okay, so this is the resulting allocation. And well, of course, we said that we cannot have like fairness and truthfulness together. And I already said that round robin gives the F1 allocation. So, you know, truthfulness is not a property of the mechanism here. So, for instance, even for 2 agents and 3 items, so if the true values are as we see on top, then the allocation goes like that. But now, if player 1 lies about their true values of the first 2 items, round robin will assign the second item first, and then the ball to player 2, the kitten to player 1, and now player 1 achieves value, a utility of 11 instead of 10, right? So playing truthfully is not a pureness equilibrium. It's not a dominant strategy in general. Okay, now, as I said, it is known that for additive agents, round robin produces EF1 allocations. And it is very easy to see why this is the case. For the first agent, the agent that gets the very first item, well, it is clear that from their point of view, this allocation is envy-free, meaning that agent 1 considers their final bundle to be better than anybody else's, right? Because in the first round, they have the best item. In the second round, they have the best item. Third round, they have the best item, and so on and so forth. But even from the perspective of any agent I, this is an EF1 allocation. And why? Well, because let's say we look at agent 3 here, right? So if agent 3 ignores what happened in the first 2 rounds, then agent 3 can pretend to be the first agent in a new round robin run that starts at this very point. So in this round, they have the best good, and the next round they have the best good, and so on and so forth. So as long as they ignore 1 good per agent, well, at least for the agents that come before in the ordering, then this is envy-free. So overall, it is EF1. Okay. Now, well, if playing truthfully is not an equilibrium, what can we say about equilibrium in general? Now, there is always an equilibrium, and to introduce it, we need to define the bluff profile. So suppose that the agents always pick truthfully. So let's say they reported their true values, and then the mechanism gives them in every step the correct good according to their true values. And let's say that pi denotes the order in which the items are allocated in this case, where everybody reports their truthful values. Now, what do I mean by that? I mean pi is the order in which the items are allocated to the agents overall, right? So the first item in this order will be the first item of agent 1. The second item is going to be the first item of agent 2, and so on and so forth. And now pick any values that are consistent with this ordering. Note that the true values may not be consistent with this ordering, but take any set of values that is consistent with this ordering for every agent. Now, this is called the bluff profile or a bluff profile. And, well, it has been shown to be a pureness equilibrium always. And, okay, so round robin is a fairness, a fair allocation mechanism that always has pureness equilibria. And it was recently shown that actually every single equilibrium of round robin is EF1, meaning that it corresponds to an allocation that is EF1 with respect to the true valuations. Okay, but everything up to here is for additive valuation functions. What can we say beyond additivity? So what kind of valuation function classes do we examine here? So beyond additive, we have cancelable functions, where I don't want to spend too much time defining, but the idea is that they preserve the ordering, the ordering of preference of an agent with respect to the available items, independently of what has been already allocated to them. I mean, clearly this is the case for additive functions. So cancelable functions are a superclass of additive, but it's a strict superclass. And we are also going to focus a lot on submodular valuation functions, where the marginal value of an item, by the way, this denotes the value with respect to I of S union G minus the value of S, right? So it's the value that G adds to the set S with respect to agent I. So this is larger when S is a subset of T. So the larger the set, the smaller the marginal contribution of a good. And of course, one can go beyond submodular to subadditive functions, but I'm not going to talk about this here. But let's look to the mechanism itself, right? So because we're going to check what happens with round robin once the agents have valuation functions that are not additive, but then the first question that comes to mind is, well, what is round robin in this case? What should be the next item in every step, right? And even if we define it some way, do we still have equilibria, and do we still have fairness guarantees in this equilibria? Right, so for the first question is, we simply keep round robin as is, right? So round robin is a known ordinal mechanism in the sense that it only needs its agent's preference order over the items. So round robin is round robin, right? The question is, what happens if the agents participating there do not have additive valuation functions? So they still need to report some kind of preference over the items, but of course, this will not represent their full valuation function. Then, do we still have pure Nash equilibria? Surprisingly, the answer is yes, or at least we always have approximate Nash equilibria, depending on the class of valuation functions. And also surprisingly, we still maintain the fairness properties at this approximate equilibrium. Okay, so let's first look at cancelable valuation functions. As I said, this is kind of like the broadest class of valuation functions that building the allocation does not change the preference order over the allocated items for the agents. So it is very compatible, let's say, with round robin itself. So always, no matter what S is, no matter what S is, then the best good with respect to S is the best good, overall, if we look at the signal terms. Now, this means that we can define the bluff profile the same way we did in the additive case, right? Given that here it makes sense to, if they report their an ordering, the round robin mechanism follows this order, which is always consistent with supposed reported cancelable valuation function, and this very much works like in the additive case. So for instance, we give the first item, nothing changes for the order of everything else, and so on and so forth. Okay, so the bluff profile still is pureness equilibrium, and it's relatively easy to show that. And then the obtained allocation from that is EF1. And in general, all the pureness equilibria are half EF1, or more generally, all the alpha approximate pureness equilibria are alpha over 2 EF1. So we have a guarantee similar to the additive case. Now, for the submodular case, already it's not completely obvious how to define the, how the mechanism proceeds, because every time something is allocated, the true ordering of the remaining items might change, right? So, but independent of that, we are going to show that, well, we do have approximate equilibria, and they do induce fair allocations. So think of, let's do this thought experiment where everybody picks the goods according to their best available marginal value. So let's say this was like a sequential game and everybody chose their best available marginal value. This would induce an ordering over the goods, and this is the ordering we use to define the black profile in this case. And while this is not a pureness equilibrium, it is a half equilibrium. And more general, we might not always have equilibria, but we always have approximate equilibria. And what can be shown here is that whenever we have an alpha approximate equilibrium, this induces an alpha over 3 EF1 allocation. So to summarize, for additive valuation functions, we always have equilibria and they're always EF1. For cancelable valuation functions, we always have equilibria and they are approximately EF1. For submodular valuation functions, round robin might not have equilibria. Actually, it might not have anything that's better than 3 over 4 approximate. But it always has half equilibria. And they are approximately fair. And moreover, it is not hard to show that it is NP hard to deviate from a half equilibrium in general, right? So in a sense, well, they are quite stable if we also take computation into account. Now, I'm going to close with some open questions or directions for future work. Well, the question is, can we have other algorithms from the fair division literature that also have pureness equilibria? Because, I mean, here we focused on NV-free, like comparison based fairness notions, but if we had something that's value-based like MMS, then the existence of equilibria would directly imply the fairness guarantees there. And of course, another question is, well, EF1 is kind of easy to achieve in the algorithmic setting. Can we have something stronger than EF1 here when we have incentives? And we know that for the additive case, it's possible to achieve EFX in equilibria, have mechanisms that always have equilibria, and these are EFX. But nothing is known beyond additive or beyond 2 agents. And of course, could we even go beyond submodular valuation functions here and say something stronger for submodular or something that goes as general as subadditive or general monotone functions. Thank you.